It was the same exact thing.
Yes. If you're trying to find the surface area,
Right.
yes. There's a simple formula if it can be written that way, okay? Now, you can extend this idea where if you have the same situation happening, but this time, let's say x is some function of this time y and z. And I should point out, the reason why we use g here is because f is already being used as this scalar function f. That's why we're not writing this as f of xy. We don't want f to represent two different things in our problem. So we use g here. So what if instead of being able to write z as a function of x and y, we can write x as a function of y and z? How do you think this changes? This will be f of what? G of yz, y, z, square root, 1 plus. I'm just going to write, I'll do it in order. That's the same notation, isn't it? Partial g with respect to y plus partial g with respect to z squared dA. See how it changes? And then the last one, I won't write the formula down. I'll just say what it is. What if y is some function of x and z? We'll have what? F of x, g of xz, z, square root, and then this partial becomes partial with respect to x, and that one becomes partial, well, it stays partial with respect to z. Understand? I'll give you two examples of those two cases. If you write x is equal to square root of y squared plus z squared, or you write y is equal to square root of x squared plus z squared, and let me put the first one up here. Z is equal to square root of x squared plus y squared. The difference between all those is just the direction in which the cone opens, right? This cone goes up like this. This cone comes out the x-axis at us, right? This one comes, what, out the y-axis like this? Right. X, like that. There's my x-axis. I think you understand. Do y'all see that? Okay. So if we have this scenario, we can use that formula, or this scenario, that formula, so on and so forth. I believe the next example I have here is going to allow us to practice with this. Can you all believe we only have two more class periods? Find the surface integral over the surface S of x with respect to the surface area, where S is the surface shown below. Okay, this is tied into why I gave you that handout and why we took some time on it, right? That's really big. Okay. I want to find the surface area, the surface integral over the entire surface, which means that we're going to need to do it one surface at a time. And you can look at this as, we're adding up the temperature along the outside of this object if it makes it easier for you to understand. So we want to find the total temperature on this side, total temperature on the outside, and total temperature on the back side, right? So what would you like to start with? There's three surfaces, right? We have, let's call this one S1, let's call this one S2, and let's call this one S3. That okay with you? All right. So what about oh, you want to start with S2? Okay. What about S2? It's in the YZ plane. Can you tell what its radius is? It's a circle, right? It's 1, and you know that because this right here, the green one, look at the equation of it right here, right? The radius is 1. So you know this has a radius of 1. The equation of that is x is 0, right? And now we have to really think about what we want to do. We can do this easy or we can do this hard. Here's the hard way. The hard way, and I won't work through the whole thing, the hard way would be to come up with my R of uv, which draws that, which we practiced, and we should all know how to do this. You want to help me? 0. V cosine u, V sine u, u's between 0, 2 pi, v's between 0 and 1. This will draw me circles with a changing radius. The radius is going to change from 0 to 1, so it should draw me that entire disk, right? Once I've got this, I can go to my formula. I could find the partials of this. Let's call this sub 2. I could find the partials of this. I could cross them, find the magnitude. I could do all that, right? And just plug things into the formula and go. But maybe this is a special case. Maybe it's a special case. Is that back part, that circle on the back side of this, is it z equals a function of x and y? So is it like a surface like this? Like, is it a surface up here like this? No, it's not a function of x and y. Is it a function of x and z, which means that you come out the y-axis? Is it a surface this way? No. Is it a function of y and z? Yes, it actually is. Your x value, right? Your x value, you could look at this as a function of y and z. It's actually g of yz, but what is the function? 0. It's 0, isn't it? Understand? Sure? If that's how simple it is, if that's our function, then what does our formula double integral over S2, because we're only talking S2, of f of x, y, z, magnitude, well, you know what, give me the short formula, the shortcut formula. It would be square root of 1 plus partial g with respect to y plus squared plus partial g with respect to z squared, right? That's what it would be, dA? dA, yes. I need to change one thing here. We're going to call this D2, all right? Because it's the domain that draws this surface, and change this to D2. It turns out that S2 and D2 are exactly the same here because it's flat, right? What is the partial of g with respect to y? 0. What's partial of g with respect to z? 0. So that's just what? Square root of 1? Which is just 1. Double integral over d2. Now I need to plug in to my scalar function, x, y, z. What is my scalar function? X, right? I need to plug in what? 0. Right? X is 0. You understand that? This right here is just x. So I replace x with whatever x is on this surface. What is x on this surface? 0. So this becomes 0 square root of times square root of 1 dA, and what's the double integral of 0? 0. All right? Now, I'd like, since this is our first surface and our first example of using the shortcut, I'd like to show what that would have been the long way, but I'm going to go quickly through it, okay? Can I show you the long way? All right, the long way I would have had to have taken this and taken partials. What's partial of R2 with respect to U? I know that's weird notation. So 0, negative V sine U, V cosine U. What's the partial of R2 with respect to V? 0, cosine U, sine U. Cross these. Cross them. So here, what do we get? Negative V sine squared U minus V cosine squared U. I'll take care of that on the next step. Next part. What? 0, which 0, 0, so 0, and then where am I? Hold on, I did this one 0, 0. So 0 again. And what is that? Where? Oh, sine squared, yes, thank you. Factor out a negative V, right? Pythagorean. So negative V, 0, 0. And now take its magnitude. And you get what? Square root of V squared, which is absolute value of V. But V is positive, right? So I don't need to worry about the absolute value. Okay, so that's the cross product, right? And what else do I need? What? I need to evaluate my scalar function on the vector curve. It's 0, right? Because it's x. So I come in here and I plug in 0 and I'm done. Now, I could have avoided all this by noticing that x was 0 and that was the scalar function. But I just want you to see what work it would have required instead of how quick it was with that shortcut. Okay, any questions? All right, let's now go and do S2. Or that was S2. You want to do S1? Okay, let's do S1. Why is that not wanting to come back here? Okay, which one was S1? The blue one? Okay, the blue one, S1. So how would you like to handle this? You want to go, R of UV, or can you look at that as being some function of two variables? Function of two variables, right? S1 is actually just x equals 1 minus z, which again is a function of y and z, isn't it? X is determined by y and z. Now it turns out that our function doesn't need y in it, right? Y is not in there. But x is determined by z for sure. So I've got this. I've got double integral over, let's call this d1. Okay, d1 is going to be the domain that draws me this surface. Now I plug in what? The scalar function. I replace x with, well, x is this, right? So 1 minus z. And then square root 1 plus partial of g with respect to y. 0 squared plus partial of g with respect to z. -1, but then squared dA. Got it? Which is root 2. Take that out of the double integral. Root 2 double integral over d1 of 1 minus z dA. Now, this is a critical juncture we're at here. Does anyone have any questions on what I've done, though, thus far? d1 are the restrictions on my double integral that will allow me to draw that blue piece, right? 1 minus z is just the entire plane. Remember, this x equals 1 minus z is a plane, isn't it? I don't want to draw the whole plane. I only want to draw the part of the plane that's in blue. So how do I restrict my y's and my z's to draw just the blue part of that plane? Drum roll. -1 to 1 on both of them would draw me a square. So look at it this way. You've got that piece right here, and I'm kind of like transposing. My x-axis comes out like this. Here's my y, right? We're taking that and we're looking at its projection down onto the yz plane. That is a polar region on the ground, isn't it? I'm going to convert this integral to a polar integral, or cylindrical, however you want to look at it. Because I can't restrict y and z to make that nice. But if I go polar, I can. So I'm going to have my theta between where and where? 0 and 2 pi. And my radius should be between 0 and 1. Right? What are the substitutions I'm going to make? This is critical that you... Because if it's a normal polar region, we go x is r cosine theta, y is r sine theta, right? This time, we don't have x, right? It's y and z. So it'll be y is r cosine theta, z is r sine theta. Yes? And look at your integral here. It just has z in it. So I'm going to make this 1 minus r sine theta r dr d theta. I'm getting nods of approval, which is why I'm continuing here. Root 2 integral, now I'm going to change it 0 to 2 pi, 0 to 1, 1 minus r sine theta r dr d theta. Remembering that when we did this over here, we are going to let y be equal to r cosine theta, let z be equal to r sine theta, because our region projected down onto the yz plane is polar, and it's in the yz plane, not in the xy plane. And then you could distribute through, right? And integrate. Do we want to take it the whole way? No? You don't want to take it the whole way? Okay. So can I dot, dot, dot this? So we get that. We're not going to be able to get a final answer then. You're just going to have to do that on your own, all right? All right, that's S1. We still have S3. Now look at S3, which kind of looks like this. Not too bad. It's not so bad, right? S3? It's pretty good. Can you write S3 as a function of two variables? No. There's just no way you can do it. You can't look at this as, anytime you can write it as a function of two variables, it's going to look like some surface that you go straight down onto a plane. It's going to be a nice shadow. Here, you can't, right? Because it wraps around itself. So you have no choice but to use the R of uv here. You've got no other option. Do you all understand? Okay, well, let's do it. I know you can do this. How are you going to draw that? I'm sorry? I didn't hear.
We did it last class.
We did something like this last class, right?
Yeah.
Or was it this exact one?
No, it wasn't this exact one. It's similar.
Okay, so look, if we look at it from this way, right, it's the green part. So it's just the edge, right? So I know I'm always going to be drawing circles in the, what plane? In the YZ plane, I'm drawing circles. It's just that the X is going to come out and go back in different places, right? So how do I draw a unit circle in the YZ plane? I've got to use these, right? So cosine, what do you want to use? U. Sine U. That should draw me unit circle in the YZ plane. And then the V, right? The V here. And you'll control it in the inequality, right? So U is going to be between 0 and 2 pi to draw me circles. And then the V is going to be, well, what's the smallest V I can have here? V is my X value, right? So 0 all the way to the back. And then the front side, right? I want to go everywhere between here and here, right? Pick points. I'm going everywhere between here and here. And that's got to land on this plane, right? So what? 1 minus z. But z is sine u. There it is. I forgot to put v here. All right. Partials cross magnitude. Set up integral. Partials. Partial of R3 with respect to u, 0, negative sine u, cosine u. Partial of R3 with respect to v, 1, 0, 0. Ooh, beautiful. And cross them. Zero. Negative cosine u. Hold on, I'm just writing down. It's positive? Definitely, okay. We're going to square it anyway, right? When we get the magnitude. All right, what's the last one? 0? Sine u. Sine u. Oh, wow, okay. Is that going to be 1? Magnitude? Root, what? Cosine squared u plus sine squared u? Yeah, well, what? Is it negative? Are y'all changing? Okay. Okay, and that's just 1, right? Where? Root cosine squared. 1 plus. Not for magnitude. You're thinking of that shortcut thing. Yeah. No, we're just looking at the magnitude of the vectors, the square root of each of the components squared added together. All right, well, that's nice, right? That works out pretty good. So now let's set it all up. We have our double integral. We're going to be going over the region D, all right, D. which is the restrictions on u and v. We have x, right? Our scalar function is x. So I need to plug the surface equation. I need to replace the x with v, because that's the x component. So v. Then I need the magnitude of the cross product, which we know is a 1. Then dA, which is integral from 0 to 2 pi. I don't have a choice with the order here, right? 0 to 1 minus sine u of v dv du. Right? Dot, 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 or continue? Dot, 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 okay. Antiderivative 1/2 v squared, plug in, ooh. All right. Do you have the idea here? So when you're doing these surface integrals, you always want to look, can you do a shortcut? If you can, do it. If you can't, then you've got to do this. And then you would add up all those answers, yes. I didn't discuss it, I didn't put it in the notes, but if your surface, right, if you have some surface S that can be broken up into smaller pieces, right, S2, S3, if this is all S, then if you're going to do the surface integral over S, you can basically say that's equal to the surface integral over S1 plus surface integral over S2 over S3, put them all together. Even if those surfaces come around each other and close in a solid, that's fine. All right, we're going to move on. So we're going to get into vector fields again. We need to establish a few things first. An oriented surface is a two-sided surface. And then I put in there just for fun, there are examples of one-sided surfaces. A surface with one side. Anyone ever heard of a surface with one side? Yeah? What is it?
Mobius strip.
A Mobius strip. We'll do a quick example. There we go. So this is a surface with two sides, right? And we're not going to argue that the edge here is a side, and this is. You could argue that there are what, like 6 sides to this? But let's just say one side, two side, yes? So if you take this and you twist one end, keep the other one fixed, twist it, and then paste this together like this, you get what's called a Mobius strip. And if you look at this and look at my index finger and my thumb, they appear to be on 2 different sides of this. But if you follow the paper around, you'll come around back to your thumb, and then you keep going, and you'll come back to your index finger, and then you'll be back to your thumb. So my thumb and my index finger are on the same side of this. So it's a one-sided surface. Kind of interesting.
I feel like that's out there. You can't say that. How can you say that?
That's an example right there.
Obviously two-sided.
I think I would have to ask you to prove to me it's 2 sides. You won't be able to distinguish the 2 sides from each other. Yeah. There's an even more advanced problem where what you do is you take that same idea, right? Well, let me try this first. Imagine this sheet was kind of like stretchy. Okay, so what would happen if I take this side and paste it to this side, right? That would be a 2-sided surface still, right? And what happens if I take this edge, this circle, and I stretch this thing around to this circle, and I make this circle be like the same as this circle. Stretch it around like that. Then what would I get? A donut, right? We call that a torus. Okay, so let me back this up. What would happen if I go twist this and put them together? I get this Mobius strip, right? But at the same time I do that, I got to back this up. Sorry. I'm going a little far away from class right now. Call this side A, B, C, and D. So when I do the torus, what I'm doing is A and C are becoming the same point, B and D are becoming the same points, right? And then I'm letting this edge go get wrapped around to this edge. Yes? That's your donut. When I do a torus, I switch these, right? So A is going to go to D and B is going to go to C. I want to do that, but at the same time, I want this edge and this edge to go to each other. Now, I can't do it, okay? I can't do it, but if you could, you'd get what's called a Klein bottle. And a Klein bottle is a four-dimensional object, and it's an example of a volumeless container. It's a solid with no volume. Just like the Mobius strip is a surface with one side, it's a volumeless container. It's weird. This is all studied in a class called, if you're interested, if you ever have the opportunity, topology. Not topography, but topology. Usually you wouldn't see that unless you're a math major. But interesting stuff. I spent like a year studying the difference between a coffee cup and a donut. And at the end of it, there's really nothing. There's no difference, okay? But it begs the question, I mean, like, what is the difference between a coffee cup and a donut? I mean, we obviously you can eat one of them, right? You can eat one, you know, I mean, there's all these differences that we can say physical descriptions, right? But mathematically, what's the difference? And so the question is, what do you mean by mathematically, right? And really what it comes down to is that they both, here's a donut, three-dimension, that's not a very good donut. There's my donut, okay, you get it? And then here's my coffee cup. There's my coffee cup with my little handle on the edge. These are mathematically the same objects. There's no difference between the two. And the reason is if I draw arbitrary curves on this donut, that curve, I can shrink it down to one point without cutting through any part of the donut, right? That curve right there on the outside. But if I draw a curve that goes into the donut, comes back around the outside and goes like this, I can't shrink that down to one point without cutting the actual donut. And the same exact thing happens on here. I can draw curves out here that I can shrink down. I can even draw curves on the handle that I can shrink down. But there are some curves that I can draw around this handle, and then there's even the one around the cup itself, right? Which I cannot do it. So it's kind of like the piece of paper. You can deform it. You could deform a donut, or probably the other way around. You could, well, I don't know what makes more sense to you. I could turn this into this if I was allowed to deform them without cutting it or tearing it. Or I could deform this back into this if I'm allowed to like move things around. So they're mathematically equivalent. That's what topology gets into. I mean,